Well, let's get started. So I'm delighted to welcome Professor Christa Gall to UAC for our colloquium today. Christa did her PhD at the University of Copenhagen as one of the very first doctoral students at the new, at the time, Dark Institute for Cosmology, and she got her PhD being knighted with a lightsaber, which is amongst the cooler things you could possibly do. After that, she came over stateside, was a NASA postdoctoral fellow at Goddard, working with Ellie Dweck, before moving to our house in Denmark, and then returning to the University of Copenhagen, where she is now an associate professor. I first learned about Christa's work when I was a grad student working on Type 1a cosmology, and Type 1a cosmology people are pretty simple. You know, you measure a distance, you measure a redshift, and you're like, we can solve all of the cosmology. But it turns out there are systematics like dust. And we're like, well, we can describe that with two numbers. And it was pretty obvious somewhere in the middle of my grad school that that was probably wrong. And we didn't have a good answer for how dust was. And so I started looking at the literature, and there wasn't much literature on dust on Type 1a supernovae, but there was a lot of literature on dust on core-collapse supernovae. And essentially all of that literature was a tremendous body of work from Christa, who could have summarized all of it with, it's not that simple, you dummies. That might also be the title of our talk today, but hopefully she also tells us how to fix all of our problems for future surveys. So Christa, please take it away.
Thanks, there's a lot of pressure here. But thanks a lot for inviting me here, that I can be here, and I really appreciate it. Also, I'm happy to having been able to very smoothly immigrate to the US, at least for a short while. I have to say they were most interested in when I was going to leave again. So I'm going to leave on Saturday. Is there any kind of other things?
A stick? Does a stick behind you?
So yeah, as Gautam said, I wasn't quite sure what to talk about, so I'm maybe covering a lot of topics here. And the one is just to mention very simple that, I mean, I guess you all know, since you're now all astronomers, that our universe is very diverse and there are many, many objects in it. And why we sometimes focus on the biggest galaxies. So we can go from the biggest galaxies we have stars in it, we have exploding stars in it, and we can go down from the really largest case to the very smallest case, where we look at just single atoms or dust. So what I'm gonna try and round up in some way is to address what is cosmic dust. And as Gautam said, I always wanted to give a talk with the title, Dust is not a parameter. So it's a bit more complex than that, and I will try to get you sort of a sensation about it. So what is dust? Dust are small solid aggregates. They form out of atoms of metals, carbon, oxygen. We'll come back to that. And they do something to us in our almost everyday astronomer life. And that is that they absorb optical light and they re-emit it in infrared light. So that means some things they are getting dimmed or we not see them at all, while in other wavelengths our objects may be very bright. How can we figure out about dust? Well, we have either emission from the thermal emission from dust grains, because they do have a temperature, or as absorption features, which we can see in the signatures of various objects we're looking at. Another way is also to look just at the depletion of elements in the interstellar gas, but that is something I'm not going to address much here. What have been always very curious about is how and where is dust formed, and that is not a question that's answered yet, but also how does it evolve in galaxies. And so that kind of also comprises the entire complexity of it. The other part, which is going to be part of this talk, are supernovae, in the sense that are mostly looking at the exploding stars. So supernovae mark the death of end-message stars. They have one thing that's interesting, and that is that they produce the heavy elements that we need for our dust, and they eject them also in the interstellar medium of galaxies, same as the dust. And then at the end, if there's still a bit of time, I would like to go into dusty business of cosmology because it got me somewhat curious about how actually the complexity of dust enters something that is very fundamental to our inner workings of the universe. So starting with the composition of dust, if I'm saying something that's all familiar to you, let me know. If I'm saying something that you don't know at all, please also, I guess, feel free to ask any questions. So depending on where dust grains can form and the environment of it, what elements are available, we can form many, many different species. And the most abundant one is sort of if we have we have carbon-rich environments or oxygen-rich environments, then we can form in a carbon-rich environment, obviously carbonaceous kind of dust grain types, and there are different ones available that I can form, giving also different structures. And in an oxygen-rich environment, we form mostly silicate type of dust. So these dust, as you can see, these are dust grains under the microscope. Usually dust grains are very small, so they can be of order of 10 nanometers up to several micron. Here you see a scale of a 1 micron carbon size dust with some amorphous structures. Silicate dust grains can have any kind of dust grains can have about an order of these sizes. So when dust grains, of course, since they are small, they cannot get very hot. They also usually don't form at very hot temperatures. So we have sort of a sublimation temperature or that defines what kind of dust can survive in a given temperature environment. And what we're finding is that typically carbonaceous dust can be at higher temperatures, so it can either form there or can survive there with a limit. Here, I think that it's put more 1,700 Kelvin, more like 2,000, 2,500 Kelvin. pHs are also a bit more robust. On the other hand, silicate dust grains they evaporate at the lower temperatures. So if you find something that gives you signatures of 2,000 Kelvin, it will not be silicate dust. It will probably likely not exist. The main thing is some dust feed has some spectral features, very prominent features, usually also more at the longer wavelengths. But in most cases, dust is fairly featureless. A little bit to the structure, like if we have carbon rich, as I said, the main prominent sources are graphite. These are sort of, you know it from the pencil, sort of a more layered structure. Then we have a diamonds, that's the toughest crystalline structure that can form. But also you can have something more very amorphous structure, so that's a bit more chaotic structures. The smallest dust grains, probably one can say is a PAHs. So these are polycyclic aromatic hydrocarbons. These are molecules in a sense. So the smallest molecules are these benzene rings of 6 carbon and 6 hydrogen atoms, and they can form to larger molecules. Up to I think one of the largest one that you have 222 carbon atoms and 42 hydrogen atoms. And then if the molecules are large, if you grow them large enough and you stick them together, at some point you reach a size that you would consider now it's a carbonaceous dust. For silicates, so if you form dust in a more oxygen-rich environment, so you have more oxygen and silicate available for the formation of dust, then the very typical structure is that you have this crystalline silicate tetrahedral structure, where it's an SiO4 molecule that forms the base of most of the silicate grains. And as well, so you have a more sort of ordered structures in the crystalline form, and you can also have a more amorphous silicate with a more chaotic forms where you can also have more inclusions of other elements, like for example iron inclusions in silicate dust. So these are sort of the very sort of rough basic structure. Of course, it gets indefinitely more complicated at some point, but let's try not go there. So just a little bit about the dust cycle, the production and the destruction of dust. So how does it look like on a very, very basic scale? Is that we have on the production side, we've been looking a lot of it, and there are, in principle, we have the stellar sources. We also have non-stellar sources. The stellar sources, the most common, we have a core collapse supernovae. Those, they produce the elements, and we have indication that they also produce the dust, and they which then get released into the interstellar medium. You can also form, like we've talked about Kant, and I was like that, is Eta Carina, which is one of the sort of luminous blue variable stars, which shed off about 40 solar masses before it hasn't even exploded yet. But all these structures here, what you have is dust. So we're finding about 0.4 solar masses of dust just in the circumstellar material. And then you can have a lower mass stars like AGB stars, the asymptotic giant branch stars. They also form some elements, not a lot, but they form dust in their wings, and which is also released into the. So all these dust grains contribute in various forms and versions because there are different environments and conditions where dust can form. So you will also have ultimately different structures and sizes of dust grains. Then in the interstellar medium, we have typically in a rough scale now, can say 3 different phases in the ISM. We have a hot phase, a hot ISM. There, if you inject dust grains there, they will be mostly affected by sputtering or evaporation processes. That means that you have a larger dust grain will get sputtered. Some grains and atoms will get kicked off the dust grains. They might also turn into the end into smaller grains. So we rarely observe, or we have not observed any reverse kind of a process there yet.
So I was curious about that. How does this dust not sublimate around massive stars like that?
Excuse me?
How does the dust avoid sublimation around massive stars?
How does it avoid sublimation? That, of course, it can only form when it's far enough away from a radiation, so it does not get evaporated. So typically, dust forms in a circumstellar material more at scales where it's cold enough for it not to get destroyed.
But in this case, that star's H2 region is massive, right? So
yeah, that is massive. That really is massive. 40 solar masses is massive, yes. It's true.
The dust that has been observed, is that very, very far away, or how, like, I would expect the H2 region to be much larger than, I guess, the image there.
Well, so this I don't actually what the radius is, but typically it's circumstellar material dust. You can have at the radius maybe 10 to the 14, 10 to the 15 centimeters. Something like that. That should be far away enough.
Just a follow-up question. In cold molecular clouds, when they condense into, stars, do those protoplanetary disks inherit most of the dust from the cloud, or is it produced from a star over its lifetime? Does that make sense?
So you mean where the dust is consumed?
When a cloud collapses, forms stars, do those stars inherit most of the dust in the disk
Yes.
of that cloud, or is it formed in situ within the stars?
Well, somewhat maybe both. Whether it's formed, I mean, let me just say the most different thing what happens in the molecular clouds is that we have to separate 2 processes. One is the formation and one is the growth. So in molecular clouds, you're more likely to have a growth of grains. That means you need to have seed grains somewhere. And the growth can be through either accretion of elements onto the dust grains. Like if you have small grains, you can accrete other atoms on it and grow it that way. This process is, of course, only efficient when you have small grains because of the surface density. Once grains are larger, they might coagulate, because if they collide, then they can stick to each other. So molecular clouds, at least, is cold enough environment that these processes are likely to happen. Molecular clouds are not dense enough, and I come back to that a bit later, for actually nucleating dust grains out of there. So if you look at star formation, then yes, if you have dust grains, they are super important because they act as a coolant in the star formation process. So you need to have them there already before. Whether then in the accretion disk, dust grains might likely coagulate, building even larger grains, and therefore acting then as even efficient, more coolant, that is more likely. But you're not necessarily form grains there, so you need some seeds there. Now we have got the cold molecular clouds, and then we have the diffuse interstellar medium, where like processes like shattering, dust grains can, like, either through collisions or shocks, they can be split apart into smaller grains. Again, very rarely that you have in the diffuse interstellar medium or hot phases, you very rarely observe, or actually we don't think we ever observed that dust grains actually would grow there. Then there are from the non-stellar sources that if you have a sort of, some have been shown that dust, especially for AGP stars, let's say dust can form in the winds. So, and there has been some studies about that also dust can form in outflows, or for example, AGNs or galactic outflows, but those amounts are not necessarily very prominent. So in the local universe, if we're going back now to the supernovae, which is our most interesting for the one reason that they are short-lived and they produce the heavy elements, and we have indication of dust formation. And one of our best examples to study core collapse supernova dust formation is 1987A. I guess some of you probably are too young to have seen that in real life. I still have. It was literally in 1987. There was a kid, and there was this very bright thing you could even see during the day. Yeah, it's in the LMC, so it's the closest supernovae that has exploded in our lifetime. Let's put it that way. And here, that's just as an example from our very latest JWST observations for the more near-camp filters, where you can see, where you really see nicely now you can resolve some of the structures there, which are formed by here in the inner region. You have the inner ejecta. That blue emission is mostly a line emission, and then you have also in the outer areas. We find that's more like continuum emission from a lot of dust that is actually there. There's many structures going on, and the dust is heated continuously by processes of forward shocks and reverse shocks. And so this hopefully will at some point address one of the bigger questions, that not just how much dust forms in a supernova, but also how much may survive all these processes of the various shock interactions. So that dust is?
There's a question in mind.
Oh. Right.
Oh, hey, Chris, I'm sorry, you answered the question on this very slide. I was going to say, how much dust is formed? You have it right there. Sorry about that.
Yes. So how much dust is formed in supernova 9887A? This is just more the latest observations, or like a later epochs of the supernovae. And here, this is just one thing. What I want to point out, that we usually will measure the flux in a certain wavelength band. And then depending on what instrument you have available with what wavelength range, you get different kinds of measurements. And so since dust, that's usually what the emission you get from dust is thermal emission. So that means it's dust grains at a given temperature. So obviously, if you look at a shorter wavelength range, you will not necessarily get all the dust which is cold, but you will more like get dust that is at the temperature where you're actually in the wavelength range where you're looking at. Right, so we have a Spitzer. These are old Spitzer observations, actually, which give you sort of a sense of how much warm dust there is. And then ultimately, if you want to really get to the very cold dust, and dust can cool because it's small grains. If you don't heat them, they cool also, of course, very quickly. So you find very cold dust, like with the Herschel observations. Here you can just visualize also IMA observations, where you clearly see that in the center, that's the supernova dust that formed in the ejecta. And how do we find out this? And that's one of the things. It is like, even we have really good data, sometimes the model and the way we figure out how much dust is there is very simple. And what people typically do is this, or some version of this. We call it, we fit a modified black body to our flux data, to our emission data. And a modified black body, which means that the basic ground assumption is that you assume that you have a spherical dust grain, so spherical Cow approximation all the way through, and it radiates as a black body. And then you model an ensemble of dust grains that usually is either homogeneously or spherically symmetric distributed around your the supernova or around some flux source. And then this is the most tricky part, and we'll come back to that a few more times, is these are the optical constants of your dust grain. So we cannot really fit for grain species. We have to assume them a priori. So we have to assume we stick in here, like for example with silicates, and this kappa here, which is the absorption, the mass absorption coefficient for a given dust species at a given grain size that is wavelength dependent. I'll show you a figure of it later. And so that is one of our main uncertainties, because sometimes what we are doing is that, or maybe you have seen reading papers, is that, oh yeah, we only have a few data points, but this one here has a lot of hidden parameters that contribute to an uncertainty which we usually not account for. That's why when you see these measurements, you fairly rarely see an uncertainty on a dust mass inference, because we just can't really, we can't get a good guess of it. And also at these very long wavelengths here, dust is any kind of dust properties are typically a bit more like a power law. So we also use often just a power law approximation for the mass absorption coefficient. So you have a certain given value and then a wavelength dependent power law with a given power with a slope parameter that you can fit or can assume. Other example here on also very latest, very cool sort of JWST observations now coming more and more. There will probably be more and more paper because people have been observing various nearby supernovae. Here's a supernova, there's an EAW and there's an 4ET. They're both in the same galaxy. Actually, that's a very supernova production factory, that galaxy. And here you see it's interesting, like about the 2017 EAW, about 5 years past its explosion. What you can see here is this is one at least a fairly prominent silicate feature. So silicate dust is the only, or one of the only dust grains that have at about 10-12 micron this very prominent bump. So at least if you see that, then you can more or less fairly safely say that you will have silicate dust there. And you can fit for that. If you're like interesting, like about 20 years or 18 years for 2004 ET, you see here, this is a bit more like featureless, makes it a bit more complicated to assume what kind of grain, what kind of dust is there. Typically, what we do assume is carbonaceous dust, because we know those two are the most abundant ones. And getting there to dust masses here, about 10 to 2 solar masses, and in this case, finding here 10 to the 4 solar masses. Of course, this does still not tell you that all the dust is there, because these are now already older supernovae, so there may be a lot of cold dust. So what we're capturing here is more of that warm dust. So we still don't know where there is 20 Kelvin dust. Yes.
There was Brian Fields had a question. I think he's on raised
But
his hand.
I am.
No,
Yes.
you answered that one too. Yeah, I was going to ask if there could also be cold dust. And we think we talked about this before. You see that over time the amount of the mass goes up.
Yes.
Is that's not an accident, right?
No.
Yeah.
It's not an accident, no.
Yeah.
There's probably a reason by it, yeah. I come back to that. I'll show you a slide in a moment. I'm getting irritated. I don't know where to look. You had a question?
No, it was.
Okay. There is a different way. Instead of looking at dust emission, so the thermal emission of dust, you can also look at dust extinction. It's a bit more tricky because you need to have the right signatures. And here just some example on how it works. It was also first proposed for 1987A, where they have this is a silicon line. And what you can see is that the silicon line is somewhat blue shifted, and it's sort of on the red wing of that emission line. It's flatter than on the blue side. And how does that work? I'm just going to show you that what is the idea behind this. So this sort of blue shifting of a line, and this we sometimes call it red depression, which sounds very depressing. So, but it's more call it absorption. Is when you as an observer would be standing here, and you have now this is a very simple supernova. You have some circumstellar material around it. You have your supernova exploding here. You have your ejector expanding here, and then you expand that ejector. Your forward jog expands into your circumstellar material. So that immediately, once you hit the wall more or less, or you bump into the circumstellar material, you launch a reverse shock. So we have these sort of two shocks usually going hand in hand. In between, the forward shock always keeps sweeping up material, and behind the forward shock, you compress material a bit more. So you make it a little bit more dense than it was actually before. And when you had that circumstellar material very dense already before, then you can actually create, we call it sometimes a cool dense shell. You may have come across that term, which means you can create a region where you have the densities high enough. If you have the elements there already, and like if you remember now Eta Carina, for example, where there would be already a lot of metals there for dust formation available, then you can cool. So the higher the density, you will have more efficient cooling, and you can actually, within quite short amount of time after explosion, eventually create here a region where dust can form. And this is interesting in a sense because at that stage, like I looked here also at the supernova 2010 JL, it was a very, very massive core collapse supernova with very, very dense circumstellar material, and very massive circumstellar material around. And what we looked here is we looked sort of at the spectral sequence of hydrogen emission lines. And what you can see is that even about 26 days past peak, roughly past peak, up to about 200 days past peak, where we got our observations, you see very prominently this blue shift on H beta, and you see also that this red wing gets depressed. And that simply is because you form the line directly here. And that means like if you're standing there as an observer, and so the blue side of your line is that what moves towards you, while the red side of the line has to go through all the dust. So that gets extinguished. So you will see such a blue shift and red depression of an emission line, so the distortion of your emission line profile when you have the dust either within your line forming region or at your line forming region. You will not see this for any circumstellar dust outside, because if you look outside, then you also it will affect the blue side as well as the red side, and you will not see a difference. So you can the question that if you see a blue shift in a hydrogen line, very often people look at H alpha because it's very prominent. If you're lucky and get a more mid resolution or high resolution data, excuse me for my voice, I got a little bit sick. Then if you just only look at one line, then you have to make a guess, because there are maybe also other reasons which can cause such a blue shift and which can cause such a distortion. But if you're lucky and if you have actually a data, a nearby supernova, that you can see this pattern as emission line over a longer wavelength range, because dust, as the optical constant, are wavelength dependent. Extinction is usually wavelength dependent because there are many, many small grains. Then you see, like in this case, where you see on the bluest lines, you see very, very strong differences, and in the redder lines, there is almost nothing. So if you have that together, you can say that could be definitely an origin of dust.
For the dust that's forming in this cool dense shell, I tend to think of dust as getting a lot of processing done when the reverse shock goes over it. So if you form and the reverse shock has already passed you, are you like generally safer? Will you maybe grow to a bigger size because you're not going to get immediately blasted by a reverse shock?
That's possible. I mean, in this case, it's a reverse shock. It's very early on, right? You will have a reverse shock always also later in a supernova. In principle, you have at many different scales a reverse shock that always depends on when the forward shock, when something hits a different medium. So if you had if you have a multiple shells, for example, of circumstellar material, you have more of these structures, and you don't know. It could be that the reverse shock might actually destroy much of the dust, or even destroy much of even the whole construct of a cool dense shell, right? Yeah. And then as we're very late on, when you hit the interstellar medium, then you have very late extinction. So this whole reverse shock thing is very complicated. And it's not, I always try to say, it's not just one shock. There are usually multiple going through an entire phase of a supernova. Making it not less complicated. So if you have this emission line, then what you can do is you can infer an extinction curve. And this is what we've done for the first time here for the supernova, is that we actually could measure per every epoch with observations. We could get an extinction curve from the line emission, from the difference or from the distortion with the blue shift and this red depression, assuming that if there would be no dust, a line must be symmetric. And you can then fit these extinction curves with some dust. I got it like that. So we have been testing, in this case, we've been fitting actually different grain size distributions. We looked at carbon and silicate grains, and we run a lot of models for that. And what we're finding is that since the slope of the extinction curve doesn't necessarily change throughout, so it must be that whatever dust forms, the size distribution stays very stable. But what you can see is that extinction itself grows over time. So that's also an indication that these features here in these line profiles are not produced by any other effects. And what we are finding here is that we're finding actually very surprising. We found that the best fit we get for the extinction curve here is that we need fairly large grains, larger grains than people usually assume when they do the dust emission fitting. I don't know why, but I have an idea why, but people like to assume a dust grain of size 0.1 micron, because the average Milky Way dust grain size is 0.25 micron. But there is no real evidence that supernova dust has to be that small. So in this case, we have observational evidence that actually, at least for in this area, at this early epochs, dust grains actually must have formed larger grains, and that gives you relatively flat extinction curve. So yes.
Could it be because you're assuming that it's like spherical?
That, of course, there are some assumptions to it. Yes, you're right. It is still, we're still making some simplifications to the whole structure. The dust could in principle be forming in clumps, or it could be in some way differently distributed, and then things might actually look different. But like for the extinction curve, it's the extinction curve itself is produced by the dust grains itself. So the only thing what could happen that if you have dust in larger clumps that would mimic larger sizes, with small dust grains in clumps that mimic larger sizes, that is something we have not considered. That might as well be, that could happen. So coming here to the parameters, you can define in principle the slope of such an extinction curve. We like to use the parameter RV, which is the total to selective extinction ratio, and it's sort of kind of characterizes the slope of that extinction curve, which you can say that if you have a very large grains, then typically extinction curves are more flatter, especially in this optical wavelengths, because the grain sizes may be just as large as the wavelengths you're looking at, or they are larger, sorry, they're larger than the wavelengths you're looking at. When grains become smaller, then typically, but not necessarily, extinction curves become steeper. And yes?
So what you found from these core-collapse supernova were these large grains, high RV particles. And this is from a single supernova at a time. We're doing detailed analysis. When you fit a large number of type 1a supernovae, what we tend to find is much lower RVs, 1.7 even. So even smaller grains than you would typically find in the Milky Way. So, but once the photosphere of the supernova expands, once you set off essentially a nuclear bomb that's running into the interstellar medium or circumstellar medium, what's different about these two explosions that's causing one to have largish grains, sort of just seem to favor smaller grain sizes?
Well, sort of the main difference is that this here we talk about the dust that just formed, that still gets released into the interstellar medium. While in the 1A case, there are some saying that dust might form in the 1A, but typically what you have is you have interstellar dust that get run over by a 1A. So you're not, for 1As, you're not looking at any dust that formed in the 1A. That's the sort of the main difference here in this case. But I'm coming back to that complexity a little bit. But the main takeaway is here that clearly, if you want to look at that, we don't have Milky Way like dust. That's in that supernova. That's not just a single case, but there are other supernova where we looked at. One is even for supernova 1987A, when they've been reanalyzing the emission lines, and they've been doing a bit even more complex modeling than we've done here, also finding larger grains. Like for supernova, also a type 2L supernova, so a core collapse supernova with a dense CSM, so 17HGC. They don't have that many lines, but they also see that the extinction curves are flatter as compared to they used as a comparison a Cardelli law, parameterized Cardelli law, finding that the better match is with a larger AV, so that means also likely larger grains. We also have with a student, we have been looking at another supernova 2014 AV. It's not so clear there, but we also getting similar results that actually extinction curves there are a lot flatter than what we find typically in the Milky Way. So there is some indication that supernova produce large grains. And how that now connects together with the phase of the supernova is something I've been doing some years back, is trying to find out, okay, how is dust really now growing in a supernova? And the one way is to get all our sporadic different kinds of random measurements we have on various different supernovas at very different phases and put them on a timeline. And what it clearly shows is that not just in this case where we actually get a similar similar relation or increase of dust when we look at the extinction and the emission methods that nicely agree at early phases. But what's interesting is that you have these very early phases, so below 200 days, so below less than 1 year, where you typically find small amounts, and what's not indicated is typically also hot dust. So this is something that keeps being debated in the community of whether is it really formed dust or is it surviving circumstellar dust that's been produced before in a star. So that is something that's not really settled, but that's in the end is what we're observing. And after about 200-300 years, after about 1 year, you see sort of an increase in the amount of dust continuously for the majority of supernova that's been produced. And I can see that I put a star, I wanted to move that directly up there, which I forgot. This is from measurements from what I just showed before. They all, you've maybe seen such a plot now in various forms, but typically we cannot see this increase. And then when we look at the very, very old supernova remnants with a few hundred years, 1,000 years old in our Milky Way, then they're also generally finding that the amount of dust overall that's been produced, now given all the uncertainties I just mentioned, what kind of type of dust there may be, but it does show that the mean average value is about 0.4 solar masses of dust that a supernova can produce, and at least seems to be not being destroyed up to these epochs where we're observing them.
Brian has a question.
Yes.
Brian?
Yeah, that's just a fantastic result. That's amazing. And that's a huge amount of mass. So that's a substantial fraction of all the heavy elements made by the star.
Yes.
That's fantastic.
And that's interesting in a sense, because that is very, very important when we talk about, and I'm coming to that in a moment, when we talk about how is the dust buildup in galaxies, how can we get a lot of dust very quickly in a galaxy? Yes?
So naively, I would have thought you would need more time to make bigger grains, but you don't have much time in these core flap supernovae. So is it surprising that the grains are larger?
It is not surprising, and that very much depends on how you form dust grains, and that is somewhat of an uncertainty yet. Whether, I mean, I show you in a moment what models can do, but let me just say one thing is that while this looks super promising, right, and it kind of looks like, okay, we have a dust grow over 30 years to reach quite a fairly decent amount of dust for a core collapse supernova. sufficient to explain all the kind of dust we find in galaxies. The one thing what can be debated is whether is this really a signature of grain growth, because forming dust at these late epochs is difficult, because you actually, for the formation of dust, you have a much shorter window, because you need to have the right temperatures and you need to have the right densities. Otherwise, you cannot really nucleate dust grains. You can only grow them later on with the elements that you have available and the small seeds you might have available. The other option, the other question is here, since these are still measurements where we have not captured the actual cold dust. I mean, it's not that these are measurements that have Herschel data all over the place, right? So most of them are derived from data at shorter wavelengths, which captures more the hot and warm dust. And the big question is here, can supernova dust actually form even faster? And what we are seeing here is simply the cold dust that getting slowly optically thinner as the ejecta expands, and therefore we just more and more dust that is already present and formed even earlier that gets just becomes visible over time, right? And the reason why this question is so interesting is because now we're coming to the theory, and the theoretical models, they all show, and that's somewhat independent of what kind of theory is used, but they show that all the dust forms even quicker after about a year. Yeah, more or less, after about a year after explosion, because that is when you if you put in the physical properties of a supernova and you assume homological expansion of your ejecta, then that is when the temperatures are just right and when the densities are just right that you can nucleate grain. And we have a few theories. One is the classical nucleation theory. It's becoming a little bit outdated, but it practically assumes that you have a seed grain that is thermodynamically stable. So it's a small grain of atoms, about 1,000 atoms together. We're not asking how we get there, but we just assume that we have them. And then via accretion of more and more atoms, we just grow grains very quickly under these right conditions. Another theory is based on more chemical kinetics or molecular nucleation theory that says, okay, we form first molecules, we form smaller molecules, then we grow to larger and larger molecules until we have a dust grain available, and then we can either stick more molecules or other grains on, and we can grow them through accretion and coagulation. And here, there are some models which have been trying to do very detailed, as you can see here already, all these many species. There's a lot of interaction and radiation coming in that makes these theories usually very complex. But the theories, the best what theories can do is to still, they can produce larger grains these days, so that's good, but we still not quite match these observations. And therefore, we still have the question, maybe dust form even earlier.
So are those single zone models that you're showing us?
Mostly, yes.
Okay. So presumably there's some range of conditions and
yes. So most of those models, they assume like a type 2p, like supernovae, which means there is a thick hydrogen envelope that also protects some of the, well, or at least, it gives you some of a shield for enough density as long as you expand, and that they don't have the interaction with circumstellar material. So we don't actually really know how this CSM interaction, how that might actually can also regulate some of the dust formation.
so how seriously should we take the theoretical models here?
Well, my diplomatic answer would be like any other model.
Yeah, no, so I'm specifically asking about like the nucleation theory and so on. Is there laboratory evidence under appropriate conditions that it's predictive?
Well, there are, I mean, we're having measurements from meteorites that show, I think we discussed that before with Brian, that there are measurements from meteorites that came to Earth that show large, for example, silicate grains. From those, we actually know also all these species. So that's why we're trying to model these species. But I think the main uncertainty is how the expansion of an ejecta, also mixing in the ejecta, is still something that is uncertain. Because as I mentioned, like before, I said you can, depending on what environment you are, you're oxygen rich or you're carbon rich, right? So now, depending on whether you mix or not mix, right? You either have, if you mix, then the first molecules that always form is CO. So you have CO, you lock up most of the carbon and oxygen, and only if you have an overabundance of either carbon or oxygen, then you form either carbonaceous grains or you form more silicate grains. So, and how you treat that is not easy. So, but overall, I mean, overall, at least we agree to, okay, grain sizes, they're probably larger, and we kind of agree that within some years, we can actually form large amounts of dust. I would say that's, yes.
And I hadn't appreciated that these single zone models mostly assume some kind of like type 2P. And is this really just because they're primarily comparing to 1987A, or?
I think that was one of the motivators, and it's also simpler to treat because it becomes more complicated if you have a CSM interaction included.
Might be a naive question, but could you like reasonably assume that the total dust mass that's produced is proportional in some way to the progenitor mass of supernova?
Only to the extent of how much elements you can form. I mean, obviously you cannot form more dust than you will have elements, but even like if you look at the theoretical models, like the stellar evolution models, which can predict for various sizes of collapse supernovae, what the yields are, then you're typically still in a safe range. So with these models, you're somewhat in a safe range. And then, yeah, the rest you cannot say that an extremely massive star, at least we haven't observed it yet. I mean, well, what we're seeing here, like, yeah, I mean, 1987A wasn't the smallest star either. We see for 10GL, we see for the other type 2N supernovas of 5IP, they seem to produce after 10, 15, 13 years still some dust. And but the amounts do not never rarely below 1 solar mass.
Okay. This question, I just wanted to synthesize something you said, because it's a question that I have. You said that if it isn't kept as a multi-phase medium, then the CMEO will come together and form CU and take away all the dust material. So this is only going to happen in a multi-phase environment. This is specific to the supernova environment because of the way that it maintains its multi-phase nature in some sense, or?
Well, the thing is, like, if you look at how elements form, you take this onion like shell structure, right? This is what sort of predicts you at what phase in the stellar evolution you produce which kind of elements.
Sure, and you answered this about Eta Carinae, but about sort of being distant. The reason I have a question about that one is because it has an ongoing luminous source. So in that case, it's because there's some sort of self-shielding that allows the dust to form and shield itself and collapse, I guess, in that environment because of all the material out there.
But yeah, for Eta Carinae, I mean, you have when a star forms, you usually that has a certain metallicity. So the majority of the elements, if you form them in a circumstellar shell, they will not have just formed in the star. So maybe there is a bit of a dredge up, but usually this is material that is still available from when the star actually formed. So it's an indication of your metallicity, right? And then obviously you must have these, I mean, like Eta Carinae, it's not just, it doesn't, so that homunculus is not built as a wind, but it's a sort of, there have been a few eruptions where in one go a lot of mass has been shed off. So that sort of preserves also some of the density that may be needed, right? And then when that moves away enough, it will cool down, and then you have a right density and you have the right temperatures for some dust formation. And if you have the moment you don't have to form a lot, right? You need the seeds. And then if you have still enough elements available, you can certainly grow.
So the dust that putatively is forming at this thin shell, right? At what point in the evolution does that become visible? If the overburden is optically thin? You know, what would we be able to actually even see the dust at these early times?
Yeah.
Yeah.
If that were true
No, earlier
after,
than that, like to 100 to 300 days.
yes,
Is that optically thick? I mean, are we able to see that?
it's a good question. When do you going to see that? Well, it seems like on a 30-year time scale, maybe if that would be the case, right? So if you were to really assume that on these epochs, if I understand you right, all the dust forms at once.
Just to test these models, I mean, yeah, clearly it seems to be forming more slowly than the theoretical models predict. But
Yes.
I'm just wondering if is there any way, is it possible even to observe the dust formation region?
At the early phases, I would be super curious to point whatever along like Herschel or a sub-millimeter instrument that can capture the cold dust to see if there's cold dust there, because it's likely cold dust. If it's totally optically thick, yeah, then you might have to wait. I'm not sure how you would otherwise notice that.
Okay, so it's optically thick.
Yeah. So yeah, I'm just briefly circling back to the complexity of dust and what I mean also in that enters then the extinction. So here just to very quickly show you, these are the mass absorption coefficient or the emissivities, right, for many different kind of species. And if you were to think that, you know, an extinction curve or with the slope indicates you small grains, then here these are just the curves for different species for one single grain size. So now for each of these species, there will be, of course, a change with grain size. But as you can see, you can also, since you never have just one species, but you might have a combination of species, you have a grain size distribution. So you cannot necessarily say small grains only give you that slope, right? And as you can see, many different species might come into play. And in the interstellar medium, when grains even gets more processed, as I mentioned before, then things become just a little bit more complex. I've been very interested in trying actually to see if that is something we can get a handle on. And what we're doing recently with a PhD student, we try to use neural networks to see if we can predict dust in supernovae. And the main idea was that so we used simulated data from a moccasin, the Monte Carlo simulation of RNS nebula, and it's a fully radiative transfer modeling, a 3D radiative transfer modeling, and that allows us to calculate models or SED models of dust with various parameters. These parameters include like the location of the dust, the grain size of the dust, the grain species of the dust, or mixing of that. And so we've been calculating about 300,000 models. And just to highlight some of the challenges that we're trying to accomplish with this is like here, this is the effect in the emission. If you just take the complete same setup of a supernova dust, like a grain species, you put it at a given radius, it has a given temperature and so on. And the only thing that you vary is the grain size. And you see typically very large differences in exactly those areas where we like to observe. The other option is also, if you look at, since the optical constants, or those curves I showed you before, depend also a little bit on who calculated it, because we're using spherical approximation, we're using scattering theory to calculate our mass absorption coefficients. And also, like you see here, variations of the exact same dust species for I don't actually remember what we used here, I think some oxygen, some silicate. You can see here the silicate feature at the 10^12 micron. And I used the silicate grain at a given grain size and just used the optical constant from different groups that have been calculated. And you already see that there are some variations in the area where we like to observe. So that comprises us an uncertainty in our dust measurements that we usually don't account for. if we make our simple assumptions. And here in this case, we try to use some with neural networks, and just from this we took, I think we calculated about 300,000 models, and then from that set we had used different setups of how we distributed also with distances, the supernovae, and we isolated our training data set, a validation set, and a test set. And what you show here is the dust mass as it's predicted, and the simulated dust. And at least for some extent, we can get very good predictions. We crash usually at the lower dust mass end, and that's simply because in this case, then like we still simulate here a supernova as a light source. So we often still have a black body from a supernova radiation. And then if dust masses are very low, they're not showing really up. And that makes it a problem. So if we have dust species that are not giving us any real emission or any features, then we still have somewhat of a problem. We've been trying very recently to also overcome that and give just better, robuster estimate of the uncertainties. We use a deep neural network now to get there. And here, this is just one of this is still a work in progress, but here's just one of the examples. We used supernova 9080K, sorry, that was recently observed also with JWST. And you see here, again, sort of a more simpler form of models with some assumptions of silicate dust and grain sizes. And it can fit the data fairly well. But then if we're putting here the numbers of like in this case, just the dust mass and the grain size and the grain size and the temperature, then this is what the models give here. And at least for our neural network, we seem like not to agree. And actually, we do favor assumption of more larger grains again. And I thought that's actually very interesting. So there is still some work to be done, but we're trying to get a bit more of a handle on whether we can actually make better prediction estimate of the uncertainties of what we are actually inferring here.
And actually, before you move on from the neural networks, the inputs are just the multiband photometry.
Sorry, I forgot to say, we tested it for specifically for JWST data because a lot of data are coming up. So we convolved our SSD with all the filter bands that you have for JWST and use that then for our training input. So we hope to create here a tool that we can, with the really amazing observations we are getting there, that we can also maybe do better or more robust estimates. That's the basic idea behind. So one thing I have been always motivated, and I'm actually, so it seems like I'm talking a lot longer than I thought. I hope it's not too boring. So one thing that I've been very motivated about, and that was driving also even my PhD and entering this whole dusty businesses, that there was some time when fairly high redshift quasars at the redshift 6, which is a cosmic time when the the universe was still very young. About maybe I think a giga-year old maximum, and they found these quasars which showed a lot of dust, and more dust. I mean, similar way of inferring that there is dust also in the galaxies as we do for the supernovae. We still use the modified black body. We use some assumption about the absorption mass efficient, and in this case, using the power law to model. But what we are finding is over redshift now is that it's even at the highest redshift these days, and it's just an example, we're finding high redshift quasars, massive galaxies with enormously amount of dust. And the interesting part is that when I started doing this, that we all thought that AGB stars are the main dominant sources for dust production, and that could never ever reach these amounts of dust in the galaxies. I've been looking then into the supernova dust production and what can supernovae do, and this is from some time in the past where we've developed some chemical evolution model where we look at how you take all the processes in the galaxies like the star formation rate, initial mass function, put the starburst lengths and so on into different sizes of galaxies, and if you just use now what supernovae produce, what I just showed you before, then you can actually fairly quickly, within a very short time scale of 30 megayears, you can actually produce significant amount of dust. Here's the gray bar from the time where dust masses were observed, which was almost next to impossible to figure out how it got there. But depending on of course, your star formation rate, the length of your starburst, and the mass of the galaxy, at least within 30 mega years, you have a chance to get to very high, large dust masses in the galaxies if you not destroy, assume that all the dust that a supernova produces is destroyed right away, right? And that was a part of the prediction. And then we did some more modeling of it, also showing that in principle, if you use the productivity of supernovae to build up dust in a galaxy, you can actually get to the dust masses from different types of galaxies, from the Milky Way to the SNC, also to some diamond break galaxies at higher redshift. If you take the, so we modeled that with a Chabert IMF, and take the length of the most recent starburst and the star formation rate, you see that actually in that very short period where supernovae are most active and formed, you can build up the dust. So the prediction was that in principle, the amount of dust, the buildup of dust in galaxies follows the star formation. And that is something I think these days people seem at least to agree on, that is for starburst galaxies the case. So what we are observing now these days was with a PhD student at DARC, Daniel Langarodi. He's done a massive work on JWST near-spec observations. We took about 600 galaxies with a near-spec spectra. We stacked them, or he stacked them in here, you can in either redshift or UV slope stacks. And if you infer, you do some galaxy, the SED fitting, you can infer like the age, or in principle here in this case, it was 1 over the specific star formation rate. You can fairly assume that that gives you an indication of the age, and you can infer extinction. And this is a very complex plot, but the main takeaway here is that within 30 mega year, in galaxies, we see already some significant extinction coming up. Then you can model the slope here of the correlation. We've done that here. We use sort of a factor that relates the star formation rate density to the specific star formation rate, and it sort of assumes that you have this linear relation that with star formation you also increase the amount of dust, and you see that also in the linear. What you also show is that smaller galaxies are actually more attended, more compact galaxies, let's put it, not necessarily smaller, but compact galaxies seem to be more attended. The one thing that what's hidden here is a bit and interesting is that if we assume here Milky Way type dust, we would actually overpredict the extinction. So, and if we assume like silicate dust, which we could assume that small grains from supernovae that's produced there, then we actually can model also that factor that we can actually fit here. And that sort of gives an indication that either super efficient grain growth in a galaxy on a timescale of 30 mega years, or supernova dust actually builds up the dust in the early type galaxy. Another indication also comes from a different work where people have been looking at the extinction curve over a larger redshift range, also from near-spec data. I think about 170 near-spec data. And what they're finding here is that with redshift, it seems like that the slope of the extinction curve is changing with redshift, meaning that it's getting flatter at a higher redshift, also as an indication for more supernova dust. Going to the other end, because there's a lot of discussion about dust destruction. So how can we destroy dust, and what are the actual mechanisms of getting rid of dust again in the galaxies? We've been looking since in normal starburst galaxies, processes are super complex. So to disentangle the whole thing is we looked at early type dusty early type galaxies. Those are galaxies. We included ellipticals, lenticulars, or any other type early type spirals, and which have very low star formation rate at that point, but they are in Herschel detected to be also very dusty. And what we've done here for the first time is we tried to get out the dust removal. I'm not calling it dust destruction right now, but the dust removal time scale. And so we have here the dust to stellar mass ratio versus the age, which we got from SED fitting. And what you see here is that over time, as galaxies age, dust gets removed on a time scale of about 2 gigayears. That is interesting because we also looked at the galaxies, the star formation rates of these galaxies, and for the star formation of the galaxies, we find that the star formation rate declines actually faster than the dust declines. So that gives us some interesting, what was interesting for a bit puzzling to us. And then we also looked at the molecular hydrogen and the atomic hydrogen, and then we got some. Sorry, yes.
Oh, sorry, I'm just curious, maybe you said this, how do you age the galaxies?
That came from SED fitting
Okay.
for each of the galaxies. So what we've used, and we for some of these galaxies we got a sub-millimeter data as well, and for where we used the IROM telescope and some other, and where we could infer then the molecular mass and the atomic mass, and we also see that also those also decline with age at a somewhat similar rate as the dust decline. So now speaking about that there's such a focus on dust destruction, right? This shows you it's not just dust destruction, it's a removal of the entire ISM at a similar rate.
I was just curious, what was the redshift range of this symbol?
Good question. I think up to redshift 3.
Was it, is there any separating it out by redshift at all?
No, not in this.
So these are early type galaxies with a passively aging stellar population. What's removing the gas?
That's the question. That exactly is the question. The one thing is, but if we look at dust, then the most common assumption is, then this is what we're trying to model here. For example, accretion, so star formation, right? But since the star formation rates are very low, star formation cannot do it. It can neither remove the gas, nor it can remove the dust, because that would be just too flat. So aspiration is not a case. Supernova shocks for dust destruction also is not the case, because since the star formation rates are very low, there are no supernovae, right? So the one thing is what we are thinking is that this is an indication of morphological quenching of the galaxies, and that could be the whole removal of the ISM could maybe be either through heating of the ISM of the cold ISM and the dust, or some outflows. That's at the moment. We also were discussing, for example, possibly type 1a supernovae, but that in the end, that also depends on where the dust is located. So all we can say is that all the dust, at least, is from the inner parts of the galaxy. So it's not through merging. It doesn't come from the outside. So there are no mergers involved. So it's either AGN activity that we cannot definitely say exactly what it is, but I think it's just very, very interesting. We've done a similar test, and that maybe also shows the part of the quenching from galaxies, about I think 20,000 galaxies in the Gamma and mass assembly survey, where we're seeing same things now in many galaxies. Here in blue indicated typical galaxies that are still on the main sequence, and then we have the galaxies that move off the main sequence. And that has been somewhat of a debate how that comes to be, and we've always predicting that is an age evolution, and here in this case we can now actually show it is an age evolution. So this is literally galaxies that move away from the star formation rate dust mass relation, and as an indication likely through morphological quenching. It's not, these galaxies are not that those are young galaxies that with very slow star formation rate, and then some brain growth or whatever built up the dust. But it is dust that has been built up in a phase where star formation rates were high, and then it moved along that line. Those moved along that line. Star formation just stopped. And yeah, happy to discuss more what can be the origin, but we're finding also for all these galaxies, we're finding a similar ISM removal rate.
Yeah, we should start moving through.
Yes.
I think we're almost at time, so. Yeah.
Okay. I actually, I thought if I finish early and not come to the whole cosmological part, then that's sort of I think that my main 3 takeaways from what I've been discussing so far is that, yeah, we have supernova dust physics. Just please remember there are different kinds of grains of species. They have different properties, they have different grain sizes, and the inner combination also for the extinction, which happy we can talk afterwards, how that enters it, have different absorption and scattering properties and likely lead to different RV. And the other one is when you look at dust from supernovae, they produce large amounts of dust. Yes, there are the unknowns of how much in the end will get destroyed. So there's definitely some more work to be done. And what fraction actually gets regrown in various phases of forward and reverse shocks. So there's also some work that still needs to be done. But it looks like promising that they are major dust producers. And in galaxies, yes, dust form quickly on short time scales. In the youngest galaxies, large amounts, they are, it can get removed quickly as well. But in the majority, the dust removal is likely on much longer time scales. Cool.
We can probably squeeze in like a question or two, and then if you have more questions, why don't you join us for dinner? So any last questions for Christa in the room?
You were talking about the neural networks doing for properties. I'm curious, could we apply that to other systems like protoplanetary disks, or do the input variables only favor to the hypothesis?
No, I think you can probably apply that to anything. I mean, not the one we are training here, because that's of course that's the thing with the machine learning. It's also always valid for a given set of data. In this case, we'll be designing it now for a given set of data and given set of dust. But in principle, the models, at least from the simulations we're putting in, they don't necessarily tell you what the underlying dust source is, whether it's a supernova or something else.
Thank you.
Yeah, I did forget to mention in the intro that Christa is also the astrophysics lead in the Perimeter AI Institute in Copenhagen. And if you are interested in AI and astrophysics, she's going to be up at Sky tomorrow, so you're welcome to also come up there and chat a little bit about that stuff. If there's no other questions, let's thank Christa again. We'll probably leave from here for dinner around 6 p.m.